Hello, students. Uh, yeah, I think I'm recording. Anyway, what I wanted to do with this lecture was to talk about voltage. Talk about the voltage around point charges, right? So today we're going to talk about voltage. Now, everything that we've really talked about so far, and let's put down some equations here. So our force field, if you want to think of it that way, just like we live under a force field of gravity, electrons and protons live under a force field of Coulomb's electromagnetic attraction, right? So I've got Q1 times Q2 divided by 4 pi epsilon. I don't know if I've been using capital R. Anyway, I'll just use smaller, R squared. I think I was using capital R. Anyway, who cares? And of course, that is in the r hat direction because it's radial out from the point charges, right? And then I said, hey, let's not worry about that because that's a vector field, of course. It's a force field, so force has magnitude and direction, you know. Now, when we looked at the electric field, we said really the electric field is just for one of these two charges. We're going to figure out what the electric field is around one of those two charges and the whole profile of that electric field, that's a vector field. And then we're going to, if we want to ever find the force, we'll just assume. In other words, when we talk about an electric field, as I've always said, it's newtons per 1 coulomb, isn't it? And that's a plus 1 coulomb. So always remember that. When we electric fields, it's volts per meter, but a volt per meter is still a newtons per 1 coulomb. So it's like we're saying, when we go from the force to this, it's like we're saying, well, we're going to normalize. We're going to normalize this force. When we go over here, we're going to say that Q2 equals plus 1 coulomb. That's what we're going to say. We're going to normalize it, and so the whole electric field now is normalized to a 1 coulomb charge. So that Q2 is a 1 coulomb charge. Q1 still stays the same, doesn't it? So whatever the charge is that we're finding the electric field for, divided by 4 pi epsilon r squared, right? So we always assume that it's a plus 1. That gives us the direction so that when we're figuring out what the electric field is, we can always figure out what the direction of the electric field is because we'll just put that 1 coulomb charge in there and see what direction it moves in, right? What's it attracted to? Is it attracted to the negative voltage, the positive voltage? Obviously, it'll be repelled by the positive and it'll be attracted by the negative, right? So we always look at it and refer back to my last lecture and or the lecture before that, I can't remember, for the example that I did on that. Now, so that's what we have so far. And of course, this, I shouldn't even have put that equal sign there. What I should have put is I should have put, oh well, I should have put the unit vector in the r hat direction, right? Because it's both. They're both vectors, and they're going radially out from the charge that's there. Now, let's talk about voltage. If you remember in my example a long time ago, I actually drew that electron gun, and I can't remember what voltage I think I put 0 volts down here, and I put, what was it, 5,000, 10,000, who knows, I don't know, 40,000. Let's put 5,000. 5,000 volts up here. So we can see what direction the charge would go. If in here, I just put a 1 coulomb charge, let's say I just put a 1 coulomb charge there, right? 1 coulomb charge plus 1 coulomb charge. Where's it going? Is it attracted to the positive voltage or the negative, the more negative voltage? Well, the 1 Coulomb charge is going to be, right, that's a positive, so that's going to be attracted to the negative. So this would be attracted to that down there. If you remember the original one that I had an electron that was going through. So let's do it for both. There's the 1 Coulomb charge. 1 Coulomb charge would be pushed down there, and that tells us that the electric field lines, right, are working in this direction, right, positive to negative. But what does the electron do? Now, the electron is going to be attracted, because it's a negative charge, is going to be attracted to the 5,000 volts, isn't it? And that's why the electron, when it was coming out of here, was deflected up that way, because the charge, anyway, you get the idea. And I'm only referring to that because we also did that other example about the uranium nucleus with 92 protons, right? I'm going to refer back to that too, just to show us how this this scalar voltage field changes. Now, so that's that is your force, right? And then this, which is normalized to 1 Coulomb, really it's newtons per Coulomb, or newtons per plus 1 Coulomb, is going to be your electric field. How do I figure out what my voltage is at any point in that field? My voltage is the integral from whatever distance away from the point source I'm at to infinity. This is the definition of voltage in an electric field, right? Times E dot dr. Right, and of course E, as you remember it, is in the direction R, so that's not a problem. So that's my voltage. That's the definition. I'm just going to put a little box around that. That's the definition of voltage inside the electric field. Now, I'm going to do an equivalency to that. You know, if it's R1 to infinity, and I think everybody knows, if you look at the electric field, I've got R squared in the denominator, right? So what would happen if R squared was infinity? That'd be infinity squared, which sounds like a great name for a rock band or something. But Xfinity squared is the same as Xfinity cubed, or infinity squared is the same as infinity cubed is same as infinity. It's infinity. So if I have any finite amount divided by infinity, in other words, if I have a pizza and I've got 7 billion people sharing that pizza, how much does each person get? The answer is none. The answer is none. So the voltage way out at infinity, because the electric field is 0 at infinity, then the voltage is going to be 0 at infinity too, isn't it? Because the electric field magnitude will be 0 at infinity. I hope everybody got that. So electric field is 0 at infinity, right? So that's what that makes it. So here's what I want to do. What I want to do so that we can find the voltage at that distance R1 is I want to say this is really the negative of the integral infinity to R1 of E dot dr. And I think everybody can see that. You know, if you're looking at the area under the curve between, you know, 1 and 2, you know, let's say that I've got a thing like this, and I got a parabola, and I'm looking at the area under the curve, right, from let's say 1 to 4, then if I'm looking at the area under the curve from 4 to 1, it's a negative area, isn't it? That's right, it's a negative area because we're going the other way, and of course it is. Yeah, anyway, let's go back to this. So I'm sure that everybody knows that identity anyway. So if I have that, now let's stick some things in there. Again, I forgot to put the timer on. Anyway, this is my timer, 1 sheet of paper. Although I have been going a little higher. I've been going up to like 40 minutes, and YouTube is pushing back on me like, we're having some problems here. But they're still taking my 205 megabyte video. So let's go back to this and just examine this a little bit in more detail. So voltage then is going to be equal to minus the integral of infinity to R1, whatever that R is, of Q divided by 4 pi epsilon R. Well, I should. Okay, well, I guess we're going back to small r's now because I use small r's in the DR anyway, so I should have used the small r's. Anyway, small r, large R, who cares? So, R squared. Now, oh, I forgot. DR. Let's not forget DR, the 4 little DR we have there. So if I've got that, then let's break this out. First of all, let's get all of the constants out of that integral. So Q divided by 4 pi epsilon, those all come out of there. And what that leaves me with is it leaves me with the integral of minus the integral from infinity to R1 of 1 over R squared dr, right? And that's just R to the minus 2, and I'm sure everybody realizes, you know, that to integrate it's just R to the minus 2 would be R to the minus 1 divided by minus 1. So that's what I'm going to do. I'm going to come down here and I'm going to continue the derivation that I've got going on up here. And so that's Q over 4 pi epsilon. And then when we do this integral that I've got here, I've got a minus, right, of a minus 1 over R, because that's really R to the minus 1. I'm sure that everybody knows that. And then I want to evaluate this between R1 and, well, between infinity and R1. And then I'm going to put another bracket around there so that I've got the same amount of brackets, really, and everything going around there. Anyway, so I think everybody can see that those cancel out with one another. So we want to evaluate this between R1 and infinity. So what I get is, let's throw R1 in there first. And so it's Q over 4 pi epsilon R1, and then minus Q over 4 pi epsilon infinity, right? And I think everybody can see that infinity in the denominator makes that 0. So that really is 0. It just goes to 0. And then that gives me Q over 4 pi epsilon R1. Okay. And so that would be the voltage at a point charge. Now, let's go back to that example that we had before, where I had a U-238 nucleus, right? I had a U-238 nucleus there, and I had an electron that was zooming by that at the speed of light, and the distance that we were away from that, I believe, was 20 angstroms, right? So the distance between here and here at one point in time was 20, or I believe that was the average, was 20 angstroms. So we were using that as a distance away from there. Now, what would the voltage be at that point 20 angstroms away? Well, first of all, what is 92 protons, right, times 1.602 times 10 to the minus 19 coulombs per proton, right? Because it's a positive, and they're positives. Let's not forget that positive there. I can't stick it in there, but if there's no negative, it's a positive. So what that gives us is 14.74 times 10 to the minus 18 coulombs, right? All right, so that's 92 times the charge on an electron. And that's what the charge is going to be at that point. So let's put that in there. So 14.74 times 10 to the minus 18 coulombs divided by 4 pi 8.85. Yeah, I know, I could just write it out, but I'm not going to because you've got to memorize this. That's right, memorize it. Times the distance, and the distance isn't squared anymore, it's just that, so it's just going to be 2 times 10 to the minus 9, because 20 angstroms is really 2 nanometers, right? And there is no square on that. That's just the thing, and I get 66.26 volts. Does that seem right? Let's see. Minus 12 minus 9. So that's minus 21 minus 18. So that's up 1,000. And then yeah, that's about right. So 66.26 volts. Now, if and this, okay, so at 20 angstroms, right? Now what's the voltage at 10 angstroms? I think everybody can see that this is 20 angstroms here, and I'm going to replace it. Everything else stays the same, right? But I'm going to replace it with 10 angstroms. So instead of being divided by this, it's going to be, so anyway, it's going to be multiplied by 2, isn't it? 132.5 volts. And if we keep going and we get right close, you know, to, I mean, right now we are 20 angstroms away, right? And then we looked at 10 angstroms away. If we get right up next to that uranium atom, well, R would be 0, wouldn't it? And so the voltage right at that, at the surface of that, would be infinity. Or, you know, in realistic terms, it wouldn't be infinity, but it'd be much higher. It would be much higher. And so what we're looking at is that electron going by there, and then what is the direction of the electric field that it sees? The electric field that it sees is pulling itself in toward that. Not only that, isn't the voltage getting higher, right? Just like the voltage, the electron here was attracted to the positive voltage, right? And isn't the voltage getting higher the closer that I get to the nucleus? So the electron, you could look at it that way too, and say that the electron is now falling along the voltage potential, right? Because it's attracted. So there's a voltage potential there. It's just following that, and that's the difference. Following the voltage potential is like flying a spacecraft with the concept that you're getting closer to the sun, you're going to go faster, right? You get further away from the sun, you're going to go slower because you're in a gravity well. And this would be the same thing. This is a potential well, right, for an electron, because the electron is attracted to the positive thing. So the electron, you've probably seen these things in malls where you put a penny in and it goes around that circle and closer and closer and closer and down at the bottom and then falls in, and your parents have just lost a penny, but they've taught you centrifugal force. I hope that that's what you're thinking right now, because that's exactly what's happening when that electron is going by that U-238 nucleus, isn't it? It's going by and it's falling into the potential voltage well. Okay, I'm glad that everybody's got that. Now, the next thing that I wanted to go on to is really power lines. And I don't know if I want to start power lines now because I don't have my timer on for one thing. And this might but just be a short introduction of voltage. And we'll be talking about voltage. Now, this is for a point source, right? Point source, point source, point source. So soon enough, we're going to get into more complex geometries than point source, than point charges. We're going to start, and the electric fields around point charges and the voltage fields. Notice there's no vector on top of that. So it's a voltage field. It's like, an analogy would be, let's say that you had a scalar temperature field through, of course, the only time I sit down without my coffee, like across the uh, thickness of my coffee cup, right? There's obviously a temperature differential. The coffee inside's very hot. The outside of the cup is very cool. So if I could look at each of the individual three-dimensional points in that cross section, or really just the cross section, because it's going to be the same symmetrically for the coffee cup all the way around it, if it's a round coffee cup. So I could just look at the cross section and say, okay, well, the inside's hot, the outside's cool. And I could look at a temperature profile. And that temperature profile would really be a scalar temperature field, wouldn't it? But what if I was looking at the heat flow, right? The heat flow has direction. It's flowing from the inside of the cup to the outside of the cup. Do you see what I'm saying? This is like heat flow. The electric field is like heat flow. The voltage at any point in there is like the temperature at that point. Does everyone see what I'm saying? I hope everyone sees what I'm saying. If you don't, then I don't know how I could make it any more plain. All right. I'm going to cut this one off here, and then I'm going to start with, well, I don't know, sometime later, I'm going to start with the derivation of lines of charge and power lines and how you figure out lines of charge. So we'll start working with one line of charge where I'll derive the, where I'll derive what the electric field is for a line of charge, right? Distance radially from a line of charge. That's what I'll do. And then we're going to start looking at more than one line of charge geometries. So instead of just having one, we'll have two. And you can probably understand. So one, that's just a positive line. So two might be a positive and a ground. So we want to look at how the field flows through that type of geometry. All right. See you in a little while.